Hello again. So together we're gonna cover the parts on algorithmics and relational algebra, relational databases. I'm gonna start with algorithmics. You may not have never written in your life an algorithm using the so-called algorithmic language. So this is an example here of a pen and paper exercise that we call the algorithmic language. And I'm going to introduce what it is. It's also found very commonly under the term pseudocode. So it's not computer code that you can run. It's a more abstract description on how a computer program should be programmed using a concrete programming language. So I'm not going to obviously go into an immense amount of detail on the subject, but to give you an idea, we consider an algorithm to be a sort of black box for which, and this is the fundamental principle of computer science, you get input data, which we normally call the input parameters. And inside the box, the algorithm does its job. It reads the input parameter, it transforms the data, it performs computation, and it outputs a result under the form of data. Now, the result can be simple, like a numerical value, for example, a number, for example. And we call this form of data a scalar data, meaning it has only one dimension with respect to the mathematical meaning. Or it can be a more complex data type, multi-dimensional, and one of the most common example of something which is not scalar, which has multiple dimension, would be an array. So an array of values. Taken together, this part here, the outputs, and also just like when you do computational mathematics on pen and paper, inside the box, you might need some intermediate variables, which we call the local variables. Taken together, they form the environment of an algorithm, which is something that you will come across in the questions. An environment of an algorithm encompasses its name of the function or the procedure, the nature, and for this I'm leaving you to refer to the web, what's a function, what's a procedure, what kind of data type that the black box returns. Here it's a real number, the input parameters, and the local variable necessary in order to perform intermediate computation. If the algorithm is a function, it returns a result with the return statement. So this is what you see here is the equivalent of my diagram about the output, what's being given back as the result. There is no particular norm or rules about how you write an algorithm, how you write pseudocode, but it's very common to use this structure, describe your environment, parameters, local variable, and then the algorithm itself is encased between the keywords begin and the keywords end. There is one particular notion that I want to, purely of a notational aspect. You'll see in the questions that in a lot of them, you'll find a back arrow. Here, there, there. This back arrow is an equivalent to, semantically, it means equal. But as the equal operator to set the value of a variable. But why do we not use equal? Why do we use the back arrow? It's simply for a matter of avoiding syntax confusion. When you use the equal symbol as a comparison. And most particularly, in the case of an if statement. For example, here, if my comparison would be P is equal to 0, you have a clear difference between compare P to 0 and the statement here, which would be set the variable P to the value 0. So it's just a matter of consistency in the syntax. In a lot of programming languages, the problem is solved by, for example, doubling the equal symbol. In C or in Python, you would write if P is equal to 0 to compare, is to avoid the problem of the difference between the set value and the compare value. This algorithm is very simple. I'm not going to describe it in particular in this video. I want to add also maybe another aspect before going to a different example. You may see convenience assumption in a piece of pseudocode. Remember that this is not computer code. It's not running on a computer. This is pen and paper. Here you have an example with, we presume that there is a function called ABS which obviously provides the absolute value of an input parameter. It's an assumption which is a safe assumption. Most programming languages do offer an absolute value function, and it's a very common thing to do in pseudocode and algorithmic language design, because otherwise it would mean that we would need to define what is the absolute function and so on and so forth, and it would become too much. So don't be concerned about what is this ABS. It's just assumed as existing, as to be available in the context. What I want to talk to you about, and as an impact on multiple questions over the preparation case, it impacts the algorithmic design questions as you have here. You see that we have an array here as parameter, an array of real numbers. But we also have questions about the notion of the algorithmic complexity. It's the easiest way to cover these two cases is to talk about an array-based algorithm. And I'm going to take a very, very common example, which is solving the following problem. Finding the smallest value in an array of integers. It doesn't matter what the numbers are. They could be integers, they could be real. It's the same idea. And when we want to do this, there's an immediate question that you should be asking yourself as an algorithmic designer. Is this array sorted? So the input array of int sorted. And we're going to make the assumption that it's not. Because if it is sorted, where is the minimum value? Suppose an array of 4 integers. So I'm going to use the typical representation as in a flat array. And in here, I've got 10, 20, 30, and minus 50. In fact, let me let me even inverse the order here. It will be more coherent with the example. To the naked eye, to the human eye, obviously, the minimum value is here. It's at the end of the array. In this particular case, of course, if the array was sorted, it would start by minus 50, then 10, then 20, then 30. And to the answer, where is the minimum value in a sorted array? The answer is always the same. It's the first element of the array. Supposing that the sort is obviously ascending. In algorithmic design, we want to know very often what's the worst case scenario when you would execute the algorithm on a computer. And we want to know this with respect to when the input data grows. This is important. If we have the assumption that the array is sorted and we want to design an algorithm to get the minimum value or the maximum value, then you have an algorithm which behaves in a so-called constant time. Because regardless of the size of the array, the answer is immediate, it's constant, it's always at the first position of the array. This is called the big O notation. And here we say that providing that the array is sorted, the big O notation for the algorithm to get the minimum value is O1, or to get the maximum value is O1. If the array is unsorted, like this one here, then what's the worst case scenario? Or what do you have to do? You need to browse the whole array in order to make sure that you are looking at every single value of the array, because the smallest one, the smallest value, could be at the very end. It's unsorted. So if your array has n elements, in this particular case, you would need to consider that the big O notation is equal to ON. You need to run the code, the program, over every single element of the array in order to find the minimum value. These are questions that you find here. They are not based on arrays, they are based on linked lists, they are based on a dictionary, but the reasoning that you need in order to answer this question is identical to the one I've done on the board with an array as a data structure. Now, we want to write this algorithm. So I'm going to describe its environment. So let's say that the name of the algorithm is find min value, min val. What is the nature of this algorithm? And again, I'm referring you to Wikipedia, for example, for this. It's a function because it returns a value. And let me make sure that I'm using exactly the same syntax as what you see here. What are the input parameters? Sorry. Of course, the array itself, I'm going to call it array n for array of number, array of integers, as we said. And for a reason that would obviously be discussed inside the various courses at DSTI, an algorithm needs to know the size of an input data structure. If your input value is scalar, if it's an integer, if it's a real number, if it's a Boolean, by default, we know that it's one-dimensional. But if the input data is multi-dimensional, we need to know its size. And as such, as you see here, we normally place the size of an array which is an integer value as well. So how many elements we have in the array. Then we have the section of local variables, which when you design an algorithm is usually filled in as you start writing its actual code between the begin and the end. So this is what I'm going to do right now. I'm going to write the local variables here, and we're going to see what we need as we go along. Now, begin. We know the principle of this algorithm. It's an iterative algorithm. You need to repeat a comparison process. And every time you move to the next element of the array, you're going to compare a value against another one. So the question is, how do we start? How do we start comparing? And here, it's a very old type of algorithm, a very old beginner's computer science question. If the array is unsorted, we are going to make the assumption that the minimum value is on the first element. It's an initial assumption. It's probably not true. But as we iterate, we're going to check if the value that we looked initially is bigger or smaller than the next value in the array. So in order to do this, I'm going to need a local variable main value, which needs to be an integer because it's the same data type as what is inside the array. And I'm going to make the assumption that this minimum value, excuse me, I'm going to need to reduce this part here, is at the first element of an unsorted array. Now, arrays are conveniently indexed, usually at 0. This is the value, so 20 is the value at index 0, index 1, index 2, index 3. So I'm going to here make the assumption that array n, my input parameter at index 0, is the minimum value. But then we're going to check if this condition holds. Now we're going to need to do our iterative process. And this is a for loop. Why? Because I know where I start and I know when I stop. I start at not the first element of the array. I've already taken this. I start at the second value of the array. I'm going to need a loop variable, which starts at, sorry, not 2, at 1. So the second item of the array, and my for loop will go to the size of the array minus 1. Why? 1, 2, 3, 4 value, but the index starts at 0. So the index are going from 0, 1, 2, 3. Size A minus 1. So my local variable I, which I also need to declare here, I as an integer, will move from 1 to size A minus 1. And if I want to be completely precise, I should add the step by step of plus 1 or just 1. So every time we iterate, we increase the value of I. And then what do we do? If the current value of the array, so array of n, excuse me, at index I is strictly smaller than my minimum value. And this is why the initialization is very important here. So if you find the next one to be smaller than the one previously, then swap the minimum value to the current value that you're reading in the array thanks to the index I. And that's all there is to it. N4, and at the end, because it's a function, we return our results, return min value. And excuse me, I always write too big. And this is the end of my algorithm. Let's do it graphically. If I have 20, 10, 50, and minus 10, if I run this code graphically, and I'm really strongly advising you to do this by yourself when you're preparing the exam. We start with min value is equal to 20, array at index 0. 1, 2, 3. So initially, min value is equal to 20. Then I'm starting I at 1, 2, size of A minus 1, so 2, 4, minus 1, 3. If array of 1 is smaller than minimum value, so minimum value is currently equal to 20, but the elements at index 1 is equal to 10, so this is true. And I'm going to now make minimum value equal to 10. Then I'm getting to the N4. I'm going back to the beginning of the for loop, knowing that I has been increased by 1. I is now equal to 2. If array index 2, 50 is smaller than min value, which is now equal to 10, this is false. So we don't change the value of the variable min value. We go back up, increase the value of I, which is equal to 3, and this will be the last step. Is array of index 3 smaller than 10? Yes, minus 10 is smaller than 10. And then inside, in min value, we set it to minus 10. When we go back up, we have finished because we have reached the value of size A, size of the array 4, minus 1, 3. It's over. We debranch and return the value minus 10. You don't have to write an algorithm in the entry exam that you'll be taking. You have to read algorithms. But as I said, you have, in this example that I've just made, you have two elements of major grounds. How do we use arrays? And what does it mean to analyze the complexity of a simple algorithm? When I did the example step by step, you see that it's ON. You see that we need to go across every single element of the array. Okay, so now let's go to the database aspect. All the algorithmics can be now solved with what I've explained here. We have here, well, you have here, the schema of a sample database. So the database schema, and most particularly here, it's called the physical schema. You can see them as the tab of an Excel file. I'm going to use Didier's file here. Sheet 1, for example, could be the table, sorry, here, could be the table where you store the values for the table cinema. And then you make another sheet and you have all the columns for the tables train and so on and so forth. This is the model of the relational model of relational databases where data is stored in tables by columns in the same way that you look at an Excel file. I'll pass on the notion of primary keys and foreign keys. It's not actually really even necessary for the context of the entry exam. What we are wanting now is to query this database. And the query here is give me the address of all the cinemas which have shown movies where both Angelina Jolie and Johnny Depp have featured. Okay? You don't need to know how to write relational algebra in order to answer this question. Relational algebra, just for the sake of the explanation, is the theoretical, and it's a proper mathematical algebra described by Ted Codd, who proposed the relational model, it's a mathematical description based on the set theory on querying of operators to manipulate tables in order to extract data. It's an algebra, so it's pen and paper, but it's where the structured query language, SQL or SQL, is rooted. When you write a SQL query, behind the scenes, the syntax of SQL is transformed and understood into a series of relational algebra operations. These operations are very, very simple. You have three specific operators. One which is sigma, one which is symbolized as a pi symbol, and the third one which is symbolized as the butterfly. So this one is called either, when you name it, sigma or select. This one is called pi or project. And this one is called the join operator. The proper name is the theta join in Codd's description. But it doesn't matter. The first two, you can see them as scissors. That's just what they are. The sigma operator is a pair of scissors which cuts the table horizontally. The pi operator is a pair of scissors which cuts the columns of a table. The theta join operator is a stitching. It's like a stick of glue. It's stitching rows of two different tables together. That's pretty much it. And then you can use standard set operators, union, intersect, and so on and so forth. But particularly union and intersect. If I take the example, again, of this sample database, excuse me, I'm going to get there. And if I would be asking you, give me all the movie information, and I'm going to do this right now. Made in France. So when you query a database, the question should always be the same. Where is the data? It's clearly here. It's a very simple query in the table movie because you have the field, the column country. So what I'm going to do here is I'm going to use my scissors to cut the rows, sigma country. So I'm cutting the rows of a table, and I'm doing this based on a condition where country, the column country, is equal to, by convention and with respect to SQL, we tend to write text values in single quotes, but it doesn't matter. It's an algebra. It's pen and paper. When I do this, I'm getting all the rows from movies, from the table movie, where the condition country is equal to France is matching. So this query answers my question. Now, if I would say, give me all the titles of the French movies, I need to do two things here. I need to do what I've done with respect to the horizontal cut, getting all the rows where title is equal to France, but I also need to cut vertically the table in order to keep the column title, and only the column title. Because in here, if I only do sigma, I have all the columns. So I'm going to use pi, but I need to be able to refer to the fact that I'm going to apply pi on the result of sigma. And that's what you see in the examples that you have here. We can name the so-called result set. R1 is equal to. So in R1, which is a virtual table, in R1 we have 1, 2, 3, 4 columns. which are the ones from the table movie. But we only have the rows where title is equal to France. What I want, my final result. Now you can of course name this the way you like. Let's say I'm going to use R11. I'm going to apply the pi operator, excuse me, on R1. And I'm going to say, give me only the column title. So that in R11, I have all the French movies, but only the value of their titles. The last part, in order for you to understand what's going on here, is when we use the butterfly operator. I am not covering the part with the standard set operators because they should be fairly obvious, the union and the intersection, and they're very easy to find their meaning on the web anyway, if you have forgotten what shut out. But the butterfly, it's a bit different because it's a non-standard algebra. So, again, I'll take a simple example. Let's say we want the director names of all movies played by Brad Pitt. Now you see here, it's another matter. The data is in two tables. Because in the table movie, where we have the director name, unfortunately, we have no information with respect to actors. Actors are found in the table distribution. And between the two, and this is why the relational model is called relational, there is a relation between the two tables via the column title. This is how we're going to be able to stitch the rows together. And it's pretty much like, you know, stitching two pieces of fabric together or two cuts of paper. You need to prepare the cuts on both sides and then stitch them together. How do we prepare the cuts on both sides? You prepare them with respect to where is the data. So I'm going to start with the easy part. I'm going to start with distribution, sigma. So I'm going to cut the rows in distribution where actor name is equal to Brad Pitt. And then I'm going to ask myself, I'm going to need to stitch R1 with rows coming from movie. But before I do the stitching, I need to remove the extra material. In this, I've got all the rows matching actor name Brad Pitt. Do I need the column number of played scenes? No, I don't, because it's not a question of my query. Do I need even the column actor name? I don't. I already have all the rows here with Brad Pitt. I don't need it anymore. What I need is the value of all the movies where Brad Pitt is playing, of course, in order to stitch it to the rows coming from movies. So really, in R11, what I need to keep out of R1 is the common column between the two tables. This is part of what a relational database does in terms of query optimization. You don't need to keep all the data in memory. Once you have isolated the only column of interest, the only one or many column or columns of interest in order to proceed to the join. Then I'm going to do the same on the other side. So in R13, for example, this 12, what am I calling it? 13 in R12, I'm going to prepare movies. So in movie, I don't really apply any restriction. I'm looking at what columns are useful. Obviously, title for joining them together, and my target director. So here it's a pie of movie where I'm keeping title and the column director. And then now I've got the bare minimum. I'm going to join them together. I'm going to stitch the rows together by saying, take all the rows in R11 and join them with R12. And this is called a natural join because there's no condition here. So it's based on the fact that there is a common column. The final thing, which is not essential for you to answer the questions, and you would see in the courses at DSTI anyway, but in R13, there are 3 columns. It's the total number of columns from the both sides of the stitching. Again, it's very much like in the physical world. You have a column title coming from R11. You have a column title coming from R12. You have a common director coming from R12. SQL works exactly the same. When you join 2 tables, when there is a common columns, both columns are loaded in memory. In order to answer our question is, give me the director names of all the movies where Brad Pitt has played. Knowing that there are 3 columns in R13, we need to do a final cleanup, which is a pie, a project, R13, and we keep the column director. With all of this, you're going to be able to answer all the database question in the entry exam. I'll give you a final clue for some of you who would have never seen. Maybe a lot of you would have seen already SQL queries, but probably very few of you relational algebra. The basic structure of an SQL query is made by select some columns from at least a table or multiple, where you will apply a series of restrictions, usually based on columns, on column value, at least for the simplest type of SQL query. If you compare this to relational algebra, and that's where there's a small discrepancy in syntax and in naming as well. Select is the equivalent of the pie operator. The from clause is is unwritten in relational algebra because it's simply the list of table names that we use in the relational algebra process. And where is sigma? Which is a bit weird because sigma, when you write relational algebra, is very often called select. And the select clause in SQL matches pi. But relational algebra is more natural because you express your restriction condition first and you finish by the end product. Whereas in SQL, you need to explicit the end product, what comes out of the query, where is the data located, and where are the restrictions, which is why the reality of an SQL query execution is 1, 2, and 3, just like in relational algebra. I hope this was useful, and I wish you again a very good luck and good preparation for your entry exam. Thank you.